Hello and welcome to today's video. Today's topic is optics for infrared, for taking pictures in infrared. First I will mention refractors, then I will come to the reflectors, and in the end mention two types of unconventional telescopes that could possibly be used. First, refractors use lenses, and lenses have this thing called chromatic aberration, which means that shorter and longer parts of the spectrum are not focused in the same points, but actually on a line, as seen here. And normally they deal with that in a special way. They use several lenses and combine them in a way to minimize chromatic aberration. But most lenses are planned for the visual range, and it's not clear from the beginning what they will do with the infrared. But there are also specialized lenses. For example, this lens I've shown here is specialized for near infrared, shortwave infrared. But normally for near infrared, conventional refractors can be used. For the shortwave infrared, as I've told you already, specialized lenses exist. I haven't used refractors for that because I didn't have detectors yet, so I can't tell you from experience, but probably it can work. Especially if you filter the light, you just may have a different focus point, but you focus and it works fine. Can be more problematic if your sensor really taps a long range of wavelengths from visual into infrared, because then this spread here, shown here, will be larger. For long wave infrared, normal refractors don't work. There are specialized lenses and they are made from germanium. But doing astronomy in long wave infrared with lenses will be difficult for two reasons. One reason is the wavelength is long and stars don't shine a lot in long wave infrared, and the other reason is the only affordable sensors, the vanadium oxide sensors, are not very sensitive. That makes it difficult. Something that counts in general is that well-coated lenses minimize the light that is reflected off the lens, so that's always a good idea. Now we have a short look at the lens materials and how they affect refractive power or refractive index and the dispersion, as often measured in Abbe numbers in the industry. Here we see the refractive index depending on the wavelength, and there's two things we can observe. There are lenses with high refractive index and lenses with low refractive index, and some are in between. The other thing we can observe from this plot is that the changes in refractive index are highest in the ultraviolet and still quite high in the visual, but in the infrared they're not very high, and some are almost flat across the spectrum. For example, fluorite, which is quite a special material anyway, because it has very low dispersion. People say you can put a laser beam through a fluorite glass and you won't even see that laser beam, which is a a magic thing. From the plot on the right side we can learn something else, that actually the two things are connected. So depending on the refractive index, this influences the dispersion and vice versa. So there are no data points like this red point here in this corner, which means there are no high refractive index glasses that have low dispersion. That's just something we have to take into account. I mean, the people who are planning lenses have to take that into account. And the other interesting thing is that these data points actually build a Y shape, as seen here, which is interesting, and I can't explain to you why, but I can mention the history of the glasses. The glasses were divided into crown glasses and flint glasses. And normally in a simple refractor you combined one crown and one flint glass. Already Fraunhofer found that out. So this more or less corresponds to the crown, and this arm of the Y corresponds to the flint glasses. Then the reflectors, they have the advantage that you don't have to care about wavelengths in general. The focal length will be the same for all wavelengths. And for near or shortwave infrared, any reflectors can be used. Even the ones that have lenses, which means they are catadioptric. On the right hand side I've shown you some types of catadioptric telescopes, but my point is they're not as easy for infrared as the reflectors that don't use lenses. For the long wave infrared, lenses completely block the light, so it will be reflected off. But there are still lots of designs that don't use lenses, like Newton telescopes, Cassegrain or Gregory telescopes, Ritchey-Chretien telescopes, and Korsch telescopes. But I don't know if any amateur possesses a Korsch telescope, because they're very sophisticated designs and expensive. They use 3 curved mirrors. Here I tried to make a plot to show the curvature of the field and the comma or astigmatism, so the way points are torn, especially at the periphery of the image. And there are telescopes that are good in both, and some that are bad in both, and some that are better in one parameter than the other. For example, a Korsch telescope would be perfect because it has a flat field and an uncurved field and no comma or astigmatism, practically speaking. Cassegrain telescopes tend to have a curved field, but not much comma or astigmatism. Richey-Chretien telescope have a flat field, but tends to have some comma at the periphery of the image, and Newtons have both problems. Then I looked up about the mirror coatings and which coatings are good for infrared or good for visual or both. And Aluminium, that is most often used these days, is quite good in both visual and infrared, but it has a little dip here around 700 nanometers and a bit above 700, 800. But there are techniques to improve that a little bit. So aluminium is, practically speaking, always above 85 or so percent reflectance, so it's useful. Whereas, for example, silver is not useful in ultraviolet at all, and then in the visual it's coming to be useful, and then in infrared it's actually quite good in the reflectance, and reflects almost 100% of the light beyond 1 micron. And gold is even a little bit better in the infrared. That's why, for example, the James Webb Space Telescope has a gold mirror coating. One special case is if you're looking at long-wave infrared, you could in principle use a telescope that has no coating at all, because glass reflects long-wave infrared, and that's what you want in a reflector. But these telescopes are used only for solar observing, I think. That's also the question you may have: what happens if I have a quartz layer on top of the reflective metal? Practically speaking, nothing at all, because in the slow wave infrared the glass doesn't matter, and in long wave infrared it reflects the waves, but that's good, basically. Then I come to two types of unconventional telescopes. One is the Schiefspiegler, that didn't want to have obstruction by the secondary mirror, so it puts the main mirror, a bit skew, and then reflects the light to the side, and the secondary mirror is on the side, so it doesn't make dispersion problems. They have been used especially for planets, and some people say the Schiefspiegler is the refractor for poor people. But these days refractors became quite a lot cheaper, especially apochromatic refractors, and the optics you buy are normally very good. This is why not many people have Schiefspieglers these days. But they could also be used for infrared. Normally they tend to have quite long focal lengths, which doesn't disturb in observing planets, but you can't take a survey image with a Schiefspiegler. The other thing is there are some off-axis Newtonians, which is a similar thing. You take a part of the parabola for the primary mirror that is not the middle but a bit outside the middle, and then the waves go to the side and are reflected on a very conventional secondary mirror, and then go out to the eye part of the telescope. This is an example from the company DGM that does these telescopes. Actually, I don't know if they make the primary mirrors directly, or if they just take a parabolic mirror that is larger than the telescope and cut out a part on the side. That is often the way it's being done. You can wonder about this reflection here, if it's still 90 degrees or a little less than 90 degrees, or if this part is a bit skew also. I haven't seen one of these telescopes, so I can't tell you. But they could very well be used for infrared, like for the visual part of the spectrum. Off-axis mirrors can be bought. They are used for electronics, and then they look like this. Normally full metal mirrors with coatings of gold or silver. For example, Edmund Optics or Tor Labs, they sell these mirrors, but normally they're not very large. That's the problem. The accuracy should be fine, especially for infrared, but I haven't seen that you could buy a very large one that is larger than a couple of inches. But this has to be kept also in mind for some applications. Now, thanks a lot for your attention.